Well, then I thank you for the introduction, and I will talk about biofouling in aquaculture, and my talk will include finfish, but also shellfish and seaweeds. And in finfish culture, biofouling is limited to the equipment, while in seaweed and shellfish culture, fouling is not only on the equipment, but also on the culture species, and this is the main difference between those three. So I will talk first a bit about the seaweeds and shellfish, and then later come back to the finfish. So if we think about the impacts of biofouling, it's the increased weight we have to think of. If you have, for example, shellfish, as you see it in the middle picture, and you have ascidians attached to this will add quite some weight to your shellfish, and this could lead to the loss of your culture organism. But it could also mean breakage, for example, if you think of algae. It will also have an impact on the whole culture system you have in the water. You might need moorings with a better buoyancy, for example, if you have a lot of biofouling, especially hard-shelled biofouling, for example. So this could be quite some cost attached to having your system adjusted to the amount of biofouling you're having. In addition to the biofouling increasing the weight, you could also have physical damage, for example. So your organism might become more susceptible to parasites if you think of biofouling organism boring into it, damaging the shell, damaging the surface of the algae, for example. This could lead to diseases. It could make predation much easier. Shells are more easy to crack if they have been bored, for example. But it will also impact the aesthetics and thereby the price you gain for your product. Meaning, if you think about, for example, oysters, you surely do not want them covered in algae once they're on your plate, so you rather want to have them clean and nice. In addition, there is the question of reduction of fitness. This is a bit of a difficult one because we don't really know in all cases if the organism becomes foul because it has a bad fitness to begin with, or if it has a bad fitness because it became fouled. So this is a bit of a question what was first, but we definitely know that competition for food exists, for oxygen, for light, for space on a culture surface. We know that biofouling organisms smother your culture organism, or it can impair, for example, the valve function of mussels. In addition, we have environmental impacts, and this includes, for example, that biofouling or the biofouling settlement community can support non-indigenous species, but it will also include, for example, biodeposition below your culture that can be increased by biofouling. So there are many reasons why you want to prevent or not have biofouling in general. And there are some ways how you can prevent that. And this is, for example, by choice of substrate or culture method. So there might be some areas where it's better to culture your algae in rafts than on bottom culture systems. You could also look at the stocking density. Some culture organisms cope well with high stocking densities while biofouling organisms don't. You can also look at spatial and temporal avoidance, and here modeling of biofouling settlement and development has gone quite far by now. And we've seen quite nice results of these models so that it actually helps you to decide when to put out your culture so that you maybe avoid having the spatfall of this one very detrimental organism, or maybe you can avoid this certain area in the water where you know that this one certain organism settles the most. In addition, there are inherent antifouling metabolites that can be enhanced. This is especially true for algae. But we also know of antifouling shell coatings that can be used on shellfish, for example. And here there has been quite some research into natural antifouling compounds. You also, if you have certain husbandry strategies that you're doing regularly, you want to look at the timing of these. For example, if you restock your mussels after a spatfall of a biofouling organism, this might be better than doing it right before, for example. There are certain resistant genotypes that can be promoted or they're used. So this is one way to go. And what you always have to keep in mind is, of course, if you start with a clean seed stock, this is always better than already bringing the biofouling out to your culture plot. So there are some ways how to prevent it. However, you will not be able to completely prevent biofouling most likely. So you will have to treat at some point. And there are certain treatment options, some that are close to what naturally happens in the environment and others that we have found out. And if you think about, for example, exposure to air, fresh water, heat, these are things that are very common to intercultural, intertidal species. And here you can, for example, help to avoid biofouling that does not cope well with, for example, fresh water. You can also use organic acids or bases. And if you're in a country with cheap manual labor, maybe you can afford some manual removal. However, this is something you might not want to do on algae, for example, where it's difficult. You have biocontrol organisms. You could use, for example, sea urchins or certain fish species, and those will help to keep your plot clean. However, here it is, of course, always a risk that these species wander off, or that they, once the biofouling is removed, start eating your actual culture organism, something you absolutely want to avoid. So this would be something that you could do, but you have to weigh the pros and cons. In general, cleaning of infrastructure is very important as not to keep a reservoir of biofouling at hand. If we look specifically at shellfish, you can do pressure washing. This can be aided, for example, by silicone release coatings that you add onto the shells beforehand. You can also add abrasive medium, for example, to shellfish kept in bags that then helps to abrade the biofouling organism on the shellfish. Looking at seaweeds, they have inherent antifouling methods using blade abandonment or epidermal shedding combined with fast growth, meaning they push out the new fresh blade and at the tip, the old one sloughs off. This is something you always should also keep in mind when harvesting, that you don't harvest when this loss of parts of the seaweed is highest, so that you don't lose too much biomass. Looking at tank culture, you can use, for example, nutrient pulsing. So you starve off your epiphytes. This is something you can use if your organism can cope well with starving, but the biofouler cannot. So there are options what you can do in treatment. In general, we can say that combinations of multiple treatments work best. That means against a broader range of foulers, but also allows you lower intensities and exposure times. Meaning, for example, if you combine heat and acid, you can probably lower the temperature and use something less acidic. So this will be less harmful to your culture organism, but maybe more effective against your biofouler. However, in general, you have to keep in mind that culture species, that there is an impact also on the culture species, and that can be higher than the help against the biofouling. So you have to weigh the cost against the benefit of these treatments. So this was so far the introduction to shellfish and seaweeds. And then we're going to come to the finfish culture. And here, this is a salmon farm in Norway, one of those where I work. And what we can say about salmon farming is that here the biofouling affects, first of all, the water exchange. So if the net is blocked, then of course the water can't come into the cage as much, and you will have, for example, reduced oxygen in the cage, which can be detrimental to the fish. It can also impact cage stability by affecting the weight of the cage and the drag, meaning you have higher drag, you need better moorings, for example. It can also impact fish health if biofouling contains pathogens, and it can have environmental impacts. Again, you could harbor non-indigenous species among the biofoulers. Finally, in Norway and Scotland, there's one particular thing. This is that we have these cleaner fish present, and Norway and Scotland has a huge problem with salmon lice on the salmon, and these cleaner fish are used to remove the salmon lice. And the challenge is that the farmers believe that they only do a good job if there's no biofouling available they could eat as an alternative food source. Scientifically speaking, this is not proven. It shows that biofouling can actually be helpful, but this is the general belief. So that's the main reason why biofouling is considered a huge problem in Norway and Scotland. And the strategies currently in use against this biofouling is, first of all, we still use copper coatings on many of the nets. And while this is phased out by now in New Zealand and Australia, you still see that a lot here. However, the copper coatings won't prevent biofouling for the entire time a net is at sea, so you have to combine this with, for example, net cleaning. Some use net exchange, but net cleaning is the main strategy currently in use. This means these high pressure cleaners that you see now in the picture, for example, with the rotating discs that expel water and remove the biofouling from the net. Underwater, this looks like this, and it's conducted quite frequently, sometimes in summer every 5 days, and it can be a problem. We believe, at least what we see, the fish react to the net cleaning. You see reduced appetite, the farmers have to stop feeding. You see jumping, general avoidance, and gill irritation. And this has to do with the organisms that you find among the biofoulers. There are, for example, these hydroids, so cnidarians. You have Ectopleura larynx here in Norway, and in the Pacific region, it's Ectopleura cosia, which looks very similar and has a similar effect. The problem is that these organisms all have stinging cells, and these stinging cells can penetrate the skin, especially at the gills of the salmon, and then cause gill irritation that is visible for up to 7 days. In addition, we also see that the material released from the farm might be able to be transported to the next farm. So this is a model that we've done where we looked at the particle transport, and what you can see is that you can reach the next farm. So that means you could transport, for example, also pathogens from one farm to the next site. In addition, it also shows that the material is transported within the site. So even if you clean your cage only for like 3-4 hours, while there are other cages on site, it might be that your fish is exposed to the cleaning waste for 2 or 3 days in a row, and this can't be good. In addition, if we look at pressure washing, it is very abrasive. What we see is that if you clean your net once, you lose up to 30% of the coating in the first go. And if you do it very often, you might lose up to 90% of the coating from your nets. And in Norway, this amounts to about 1,250 tons of copper that are lost per year at sea. This is not only an environmental problem, this is also a cost that is lost at sea. So this is something farmers would really like to do something about. In addition, there's a certain risk that comes with the net cleaning, because not always these cleaners are handled perfectly, and then we see that there is damage to the net where the fish could escape through. So this is a problem. So in general, what we can say is we definitely need better biofouling management strategies here. And I would love to go into detail now, but as we have only limited time, I'm just going to show you 3 strategies that we believe could be the future. And one would be if we could develop an efficient antifouling that is so good that you do not need any cleaning. And of course, this would have to be benign and good for the environment. So this is quite challenging, but that would be a perfect solution. The other option would be to have an antifouling, also, of course, something benign that would combine with very few cleaning events. So, and in addition, maybe a cleaner that would suck up the cleaning waste, so you don't have this as an impact on the fish. Finally, there's this third strategy that has been lately been used a bit, so there's some movement towards this, and this is to groom the nets regularly, meaning you have something that looks a bit like your vacuum cleaner at home, these cleaning robots. You would use something like this that grooms the net regularly, like every other day that would go over the net and brush it, so that you do not have the chance of a mature biofouling community growing on your net, but instead have already removing the small parts of biofouling that settle first. So this would be one way, another way to do this. So yeah, there are many ways, and to sum this up, we can say that it is important to keep in mind the balance between the benefit and the cost of biofouling management. This is one that is really, we need to do more research to find out what does it cost us to get rid of the biofouling. We do see that monitoring and modeling tools are improving and are helping us to predict and mitigate biofouling. So that's a chance we should use even more. And it's important to keep in mind that combinations of treatment methods may be the way to go. There is definitely more research needed into, for example, genetic resistance, variety of culture species, especially if we think about finfish. Here, all the research is basically done on salmon. We know next to nothing about many of the other species that are cultured. Also, for example, if you think about freshwater, and also new habitats. Finfish farming is going offshore, is going to closed systems. We know nothing about this, and I'm sure there are also systems about algae and shellfish we know very little about. So here's definitely a lot of room for research. Yeah, that was from me. Thank you very much. And yeah, I hope this was informative.